Alright, in this video we will discuss protocols in Swift 4 protocols. A protocol defines a blueprint of methods, properties, and other requirements that suit a particular task or piece of functionality. The protocol can be adopted by a class, structure, or enumeration to provide an actual implementation of those requirements. Any type that satisfies the requirement of a protocol is said to conform to that protocol. In addition to specifying requirements that conforming types must implement, you can extend a protocol to implement some of these requirements or to implement additional functionality that conforming types can take advantage of. Protocol syntax. You define protocols in a very similar way to classes, structures, and enumerations. You just say protocol, some protocol, and in curly braces put the definition of the protocol. Custom type states that they adopt a particular protocol by placing the protocol's name after the type's name, separated by a colon as part of the definition. Multiple protocols can be listed and are separated by commas. So a struct, like some structure, can implement multiple protocols. First protocol, comma, another protocol. If a class has superclass, list the superclass name before any protocols it adopts, followed by a comma. So class, some superclass, comma, first protocol, another protocol, and then the class definition goes there. Property requirements. A protocol can require any conforming type to provide an instance property or type property with a particular name and type. The protocol doesn't specify whether the property should be a stored property or a computed property. It only specifies the required property name and type. The protocol also specifies whether each property must be gettable or gettable and settable. If a protocol requires a property to be gettable and settable, that property requirement cannot be fulfilled by a constant stored property or a read-only computed property. If the protocol only requires a property to be gettable, then the requirement can be satisfied by any kind of property, and it's valid for the property to be also settable if this is useful for your own code. So property requirements are always declared as variable properties prefixed with the var keyword. Gettable and settable properties are indicated by writing get set in braces after their type declaration, and gettable properties are indicated by writing get in braces. So protocol, some protocol, var must be settable is int, and then get set. Var does not need to be settable is an int, and you must define the get function for it. So always prefix type properties with the static keyword when you define them in a protocol. This rule pertains even though type property requirements can be prefixed with the class or static keyword when implemented by a class. So protocol, another protocol, static var some property, colon int, get set. Okay. Here's an example of a protocol with a single instance property requirement. Protocol fully named, var full name, colon string, get. So this protocol requires a conforming type to provide a fully qualified name, and the protocol doesn't specify anything else about the nature of the conforming type. It only specifies that the type must be able to provide a full name for itself. The protocol states that any fully named type must have a gettable instance property called full name, which is of a type string. So here's an example of a simple structure that adopts and conforms to the fully named protocol. Struct person is fully named, var full name colon string, and then let John equal person with full name John Appleseed. So John.full name is John Appleseed, so the get has been implemented. So this example defines a structure called person, which is represented a specific named person. It states that it adopts the fully named protocol as part of the first line of its definition. Each instance of the person has a single stored property called full name, which is of type string. This matches the single requirement of the fully named protocol and means that the person has correctly conformed to the protocol. Swift reports an error at compile time if a protocol requirement is not fulfilled. Here's a more complex class which also adopts fully named protocol. Class Starship. It has a var prefix, which is an optional string, var name, which is a string, an init function which takes a name and a prefix and sets self.name and self.prefix, and then var full name, which returns a string by taking the prefix and appending the name to it. And so var ncc 1701 equals starship name : enterprise prefix : USS. So the full name is USS Enterprise. This class implements the full name property requirement as a computed read-only property for a starship. Each starship class instance stores a mandatory name and an optional prefix. The full name property uses the prefix value if it exists and prepends it to the beginning of the name to create a full name for the starship. Now, method requirements. Protocols can require specific instance methods and type methods to be implemented by conforming types. These methods are written as part of the protocol's definition in exactly the same way as for normal instance and type methods, but without curly braces or a method body. Variadic parameters are allowed, subject to the same rules as for normal methods. Default values, however, cannot be specified for method parameters within a protocol definition. As with type property requirements, you always prefix type method requirements with the static keyword when they're defined in a protocol. This is true even though type method requirements are prefixed with the class or static keyword when implemented by a class. So protocol, some protocol, static func, some type method. The following example defines a protocol with a single instance method requirement. So we have a protocol random func number generator. It must have a func random which goes to double. So this protocol requires any conforming type to have an instance method called random, which returns a double. And although it's not specified as part of the protocol, it's assumed that this value will be a number from 0.0 up to, but not including 1.0. And the random number generator protocol doesn't make any assumptions about how each random number will be generated. It simply requires the generator to provide a standard way to generate a new random number. Here's an implementation of a class that conforms to this. The class implements a pseudo-random number generator algorithm known as a linear congruential generator. So we have a class linear congruential generator, random number generator, takes the last random as 42, sets up M, A, and C values, and does some remainder arithmetic for this function random based on the linear congruential generator. And so let generator equal linear congruential generator. And so we can generate random numbers as generator.random. Okay? Mutating method requirements. It's sometimes necessary for a method to modify or mutate the instance it belongs to. For instance, methods on value types, that is structures or enumerations, you must place the mutating keyword before a method's func keyword to indicate that the method is allowed to modify the instance it belongs to and any properties of that instance. This process is described in modifying value types from within instance methods. If you define a protocol instance method requirement that is intended to mutate instances of any type, that adopts a protocol mark the method with the mutating keyword as part of the protocol's definition. This enables structures and enumerations to adopt the protocol and satisfy the method requirement. if you mark the protocol instance method requirement as mutating, you don't need to write the mutating keyword when writing an implementation of that method for a class. The mutating keyword is only used by structures and enumerations. The example below defines a protocol called toggleable, which defines a single instance method requirement called toggle. As its name suggests, the toggle method is intended to toggle or invert the state of any conforming type, typically by modifying a property of that type. So the toggle method is marked with the mutating keyword as part of the toggleable protocol definition to indicate that the method is expected to mutate the state of a conforming instance when it's called. So we have a protocol toggleable with a mutating func toggle. And if you implement the toggleable protocol for a structure or enumeration, that structure or enumeration can conform to the protocol by providing an implementation of the toggle method that is also marked as mutating. The example below defines an enumeration called on-off switch, and this enumeration toggles between two states, on and off. The enumeration's toggle implementation is marked as mutating to match the toggleable protocol's requirements. So here's the enum toggleable on-off switch, which it conforms to the protocol toggleable. So we have case off, comma on, mutating func toggle, switch self, case dot off, self equals dot on, case dot on, self equals dot off. So that's the toggle function. And var light switch equals on off switch dot off, light switch dot toggle, and now light switch is equal to dot on. Initializer requirements. Protocols can require specific initializers to be implemented by conforming types. You write these initializers as part of the protocol's definition in exactly the same way as for normal initializers, but without curly braces or an initializer body. Protocol, some protocol, init, some parameter goes :int. Okay, so the initializer must follow this protocol of some parameter taking an int. Here's the class implementing some protocol, required init some parameter :int, and then the initializer implementation goes in there. You must mark the initializer implementation with the required modifier. The use of the required modifier ensures that you provide an explicit or inherited implementation of the initializer requirement on all subclasses of the conforming class, such that they also conform to the protocol. For more information on required initializers, see required initializers. You don't need to mark protocol initializer implementations with the required modifier on classes that are marked with the final modifier because final classes cannot be subclassed. For more on the final modifier, see preventing overrides. So if you have an abstract class and then you inherit from it and it's marked as final, you don't need to write the word required. But if it's not final and it implements this protocol, you need to mark it as required so that we can make sure that the subclasses also know to implement the init method. Now, if a subclass overrides a designated initializer from a superclass and also implements a matching initializer requirement from a protocol, mark the implementation with both the required and the override modifiers. So we have the protocol, some protocol init, we have some superclass init, and then we have some subclass where we extend the some superclass, implement some protocol, and so this init overrides the parent init and is required. So we're going to mark it with both required and override. Failable initializer requirements. Protocols can define failable initializer requirements for conforming types as defined in failable initializers. A failable initializer requirement can be satisfied by a failable or non-failable initializer on a conforming type. A non-failable initializer requirement can be satisfied by a non-failable initializer or an implicitly unwrapped failable initializer. Okay, that was a little verbose. We'll leave that there. Protocols as types. Protocols don't actually implement any functionality themselves. Nonetheless, any protocol you create will become a fully fledged type for use in your code. Because it's a type, you can use a protocol in many places where other types are allowed, including as a parameter type or return type in a function, method, or initializer, as the type of a constant, variable, or property, as the type of items in an array, dictionary, or other container. Note, because protocols are types, begin their names with a capital letter such as fully named and random number generator to match the names of other types in Swift such as int, string, and double. So note, it's not exactly camel cased, or rather its first letter is also capitalized. Now, here's an example of a protocol used as a type. So we have a class dice. Let sides be an int, let generator be a random number generator, and init with the sides and the generator, self.sides is sides, self.generator is generator, func roll returns an int, which will take the generator random number, multiply it by the number of sides, convert it to int, and add 1. So let's say we have a 6-sided die. We generate a random number 0.3, so 6 times 0.3, convert that to an int and add 1. So we have a dice roll. Now, this example defines a new class called dice, which represents an n-sided die for use in a board game. Dice instances have an integer property called sides, which represent how many sides they have, and have a property called generator, which provides a random number generator from which to create dice roll values. The generator property is of type random number generator, therefore you can set it to an instance of any type that adopts the random number generator protocol. Nothing else is required of the instance you assign to this property except that the instance must adopt the random number generator protocol. Dice also has an initializer to set up its initial state, and the initializer has a parameter called generator, which is also of type random number generator. You can pass a value of any conforming type into this parameter when initializing a new dice instance. Okay, so dice provides one instance method roll, which returns the integer value between 1 and the number of sides of the dice. This method calls a random generator method to create a new random number between 0 and 1 and uses this number to create a dice roll within the correct range. Because generator is known to adopt random number generator, it's guaranteed to have a random method to call. Here's how the dice class can be used to create a 6-sided dice with a linear congruential generator instance as its random number generator. var d6 equals dice, sides equals 6, generator colon linear congruential generator, and so for underscore in 1 to 5, print random dice roll is d6 dot roll, so we get 5 dice rolls from this random dice of 6 sides. Now let's talk about delegation. Delegation is a design pattern that enables a class or structure to hand off or delegate some of its responsibilities to an instance of another type. This design pattern is implemented by defining a protocol that encapsulates the delegated responsibilities such that a conforming type known as a delegate is guaranteed to provide the functionality that has been delegated. Delegation can be used to respond to a particular action or to retrieve data from an external source without needing to know the underlying type of that source. So for example, below defines 2 protocols for use with the dice-based board games. We have a protocol dice game and we have a protocol dice game delegate. So dice game protocol says we need to have a dice variable which we can get and a function play. Dice game delegate says we need to have a game did start, a game, and a game did end. So the dice game protocol is a protocol that can be adopted by any game that involves dice. The dice game delegate protocol can be adopted by any type to track the progress of a dice game. So the dice game delegate takes the dice game and tells you if the game started or ended, or a new turn started. So here's a version of the Snakes and Ladders game originally introduced in Control Flow. This version is adapted to use the dice instance for its dice rolls, to adopt the dice game protocol, and to notify dice game delegate about its progress. So we have Snakes and Ladders, which is a dice game, or implements the dice game protocol. So let final square equal 25. Let dice equal a dice, which is 6-sided, uses the linear congruential generator for its random generator. Var square equals 0. Var board is an int array. Init is going to set up the board as an array, which is going to take in repeating :0, count final square plus 1. So count will be 26. Board at position 3 is equal to plus 08. Board at position 6 is plus 11. Board at 9 is plus 09. Board at 10 is plus 02. Board at 14 is minus 10. 19 is minus 11. So basically we have the snakes and ladders, and we're setting up a couple snakes and a couple ladders. So if you hit the 20-second space, you go back 2. So you have a snake of length 2, and so on. So var delegate is a optional dice game delegate. And now func play is implemented because it's a dice game and we must implement that. So square equals 0, delegate. We check if the game did start, and we pass in self, which is a dice game. And the game loop is, while square is not the final square, we roll the dice, we do a dice roll, we check if it's the next turn, did start new turn with dice roll, using our delegate, and then we switch square plus dice roll, case final square, break game loop, case let new square, where new square is greater than final square, continue the game loop. Default is square plus equals dice roll, square plus equals board square. So we're going to move by the number of dice rolls, and then if we have a snake or ladder, we're going to add that in. And then we're going to do a delegate, optional delegate dot game did end, and pass in self. So for a description of Snakes and Ladders gameplay, see break section of Control Flow. This version of the game is wrapped up as a class called Snakes and Ladders, which adopts the dice game protocol. It provides a gettable dice property and a play method in order to conform to the protocol. The dice property is declared as a constant property because it doesn't need to change after initialization, and the protocol only requires that it must be gettable. So dice itself was a constant property using let, and the square can change, so it was a var. Now, dice game delegate provides 3 methods for tracking the progress of the game. These 3 methods have been incorporated into the game logic within the play method above, and are called when a new game starts, a new turn begins, or the game ends. So this is how we implemented the game did start or game did end, or the new turn began for the delegate during the function play. I see. So basically we have set the delegate up during the function play. Okay. The Snakes and Ladder game board setup takes place within the class's initializer. All game logic is moved into the protocol's play method, which uses the protocol's required dice property to provide its dice roll values. Note that the delegate property is defined as an optional dice game delegate because a delegate isn't required in order to play the game. Because it's an optional type, the delegate property is automatically set to an initial value of nil. Therefore, the game instantiator has the option to set the property to a suitable delegate. Now, dice game delegate provides three methods for tracking the progress of the game. These three methods have been incorporated into the game logic within the play method above and are called when a new game starts, a new turn begins, or the game ends. Because the delegate property is an optional dice game delegate, the play method uses optional chaining each time it calls a method on the delegate. If the delegate property is nil, these delegate calls fail gracefully and without error. If the delegate property is not nil, the delegate methods are called and are passed the Snakes and Ladders instance as a parameter. This next example shows a dice game tracker which adopts the dice game delegate protocol. So now we have a dice game tracker which implements the dice game delegate or conforms to the dice game delegate in Swift terms. So var number of turns is 0. Func game did start takes in a dice game called game, and then number of turns is 0. If game is Snakes and Ladders, you print started a new game of Snakes and Ladders, and then you print the game is using a game.dice.sides sided dice. Okay, func game underscore game colon dice game did start new turn with dice roll colon int number of turns plus equals 1 printed rolled a dice roll, and func game did end underscore game dice game print the game lasted for number of turns. So dice game tracker implements all three methods required by the dice game delegate. It uses these methods to keep track of the number of turns a game has taken, resets a number of turns property to 0 when the game starts, increments it each time a new turn begins, and prints out the total number of turns once the game has been ended. The implementation of the game did start underscore colon shown above uses the game parameter to print some introductory information about the game that's about to be played. The game parameter type has a type of dice game, not Snakes and Ladders, and so game did start can access and use only methods and properties that are implemented as part of the dice game protocol. However, the method is still able to use typecasting to query the type of the underlying instance. In this example, it checks whether the game is actually an instance of Snakes and Ladders behind the scenes and print the appropriate message if so. So here we check if game is Snakes and Ladders. Okay. Hopefully you remember this is keyword, which is able to do that for us. The game did start method also accesses the dice property of the pass game parameter. Because game is known to conform to the dice game protocol, is guaranteed to have a dice property, and so the game did start method is able to access and print the dice sides property, regardless of what kind of game is being played. Now here's how the dice game tracker looks like in action. Let tracker equals dice game tracker, let game equals Snakes and Ladders, game.delegate equals tracker, game.play. And so we start a new game of Snakes and Ladders. The game is using 6-sided dice, roll of 3, roll of 5, roll of 4, roll of 5. The game lasted for 4 turns. Adding protocol conformance with an extension. You can extend an existing type to adopt and conform to a new protocol, even if you don't have access to the source code for the existing types. So existing extensions can add new properties, methods, and subscripts to an existing type, and are therefore able to add any requirements that a protocol may demand. For more about extensions, see extensions. Existing instances of type automatically adopt and conform to a protocol when the conformance is added to the instance's type in an extension. For example, this protocol, called text representable, can be implemented by any type that has a way to be represented as text. This might be a description of itself or a text version of its current state. So we have protocol text representable with var textual description, which is a string which has to be gettable. So the dice class can be extended with it, so we can say extension dice with the protocol text representable, add a method textual description, or a var, which is a string which returns a sided dice. This extension adopts a new protocol in exactly the same way as if DICE had provided it in its original implementation. The protocol name is provided after the type name separated by colon, and an implementation of all requirements of the protocol is provided within the extension's curly braces. Any DICE instance can now be treated as text representable. So if we have a dice, we can do, let's say, 12-sided dice, D12. So D12.textual description, and it'll print a 12-sided dice. Similarly, the Snakes and Ladders game class can be extended to adopt and conform to the text representable protocol as well. And the var textual description can be a game of Snakes and Ladders with final squares, and we can print it and we will get it's a game with 25 squares. Now, declaring protocol adoption with an extension. If a type already conforms to all of the requirements of a protocol but has not yet stated that it adopts that protocol, you can make it adopt the protocol with an empty extension. So you have the struct hamster with a name string, textual description string, and you can extend it using extension hamster colon text representable, which is an empty extension. So this way we can state that it conforms to this text representable. Instances of hamster can now be used wherever text representable is required type. So let Simon the hamster equal hamster name Simon, let something text representable be text representable Simon hamster, print something text representable, dot textual description will print a hamster named Simon. Types don't automatically adopt a protocol just by satisfying its requirements. They must always explicitly declare their adoption of the protocol. Collections of protocol types. A protocol can be used as a type to be stored in a collection such as an array or dictionary as mentioned in protocols as types. This example creates an array of text representable things. Let things be an array of text representable equals game D12 Simon the hamster. It's now possible to iterate over these items and print them each of their textual description. So you can go for thing in things and then print the thing.textual description. Note that the thing constant is of type text representable. It's not of type dice or dice game or hamster, even if the actual instance behind the scenes is of those types. Nonetheless, because it's of type text representable and anything that is text representable is known to have a textual description property, it's safe to access thing.textual description each time through the loop. Protocol inheritance. A protocol can inherit one or more protocols and can further add requirements on top of the requirements it inherits. The syntax for protocol inheritance is similar to the syntax for class inheritance, but with the option to list multiple inherited protocols separated by commas. Protocol inheriting protocol is some protocol, comma, another protocol. So here's an example of a protocol that inherits the text representable protocol. Pretty text representable. So pretty textual representative description should be a getable property, and we can create that. So simply extending snakes and ladders with pretty text representable and creating a var for that inside, and we're making some nice pretty text. Var output equal textual description plus colon \n, and then for index in 1 to final square, switchboard index case, let ladder where ladder is greater than 0, output plus equals, and then a little triangle up and a little triangle down, or our default, and then return the output. This extension states that if it adopts a pretty text representable protocol and provides an implementation of the pretty text description property for the snakes and ladders type, anything that pretty text representable must also be text representable, and so the implementation of the pretty textual description starts by accessing the textual description property from the text representable protocol to begin an output string. It appends a colon and a line break and uses this as the start of its property pretty text representation, and then it iterates through the array board squares and appends a geometric shape to represent the contents of each square. And so here you can see the pretty text representation of the snakes and ladders game, or any instance. Class only protocols. You can limit the protocol adoption to a class types by adding the any object protocol to a protocol's inheritance list. So we'll add the any object protocol, and we can restrict it to being only classes and not structures or enums. Protocol composition. So it can be useful to require a type to conform to a multiple protocols at the same time. You can combine multiple protocols into a single requirement with protocol composition. Protocol compositions behave as if you define a temporary local protocol that has combined requirements for all the prototypes in the composition. So protocol compositions have this form, some protocol and another protocol. You can list as many protocols as you need, separating them with ampersands. In addition to its list of protocols, a protocol composition can also contain a class type which you can use to specify a required superclass. Here's an example that combines two protocols named and aged into a single protocol composition requirement on a function parameter. So you have two protocols, one for named, one for age, and you have a struct person which implements or conforms to both named and aged, var name string, var age. And then we have a celebrator which is a composition of both named and aged for wishing happy birthday. And then let the birthday person equals person, name colon Malcolm, age 21, wish happy birthday to birthday person. So in this example, the name protocol has a single requirement, the age protocol has a single requirement, both are adopted by this structure called person, and we then pass in this person to wish the birthday happy birthday to. Here's an example that combines the named protocol from the previous example with a location class. So we have a location class, latitude, longitude in it, set them up. City class which takes in location, comma named. and a begin concert which takes in location, which is location and named, and then we can do location.name or location. So we can now create a city which has a name, latitude, longitude, and begin concert in Seattle. So the begin concert in function takes a parameter of type location and named. Okay. So in a given location, and location is Seattle. So in Seattle, now passing birthday person to the begin concert in function is invalid because person is not a subclass of location. Likewise, if you made a subclass of location that didn't conform to the name protocol, calling begin concert in with an instance would also be invalid. Checking for protocol conformance, you can use the is and as operators described in typecasting to check for protocol conformance and to cast to a specific protocol. Checking for the casting to a protocol follows exactly the same syntax as checking for and casting to a type. The is operator returns true if it's an instance that conforms to the protocol and false if it doesn't. The as ? Version of the downcast operator returns an optional value of the protocol's type, and this value is nil if the instance does not conform to the protocol. The as ! Version of the downcast operator forces the downcast to the protocol type and triggers a runtime error if the downcast does not succeed. So here's a protocol has area, which has to give you an area. And so circle implements has area, and we can get the var area as pi r squared or pi rr. Init is radius, which selfs the self.radius, which is a double, and pi is set to 3.14. Class country has area, which just specifies an area. The circle class implements the area. Here's an animal, which does not conform to the has area protocol. And objects is an array of any objects, where circle has a radius of 2, country has an area of 243_610. Animal has 4 legs. The objects array is initialized with an array literal containing a circle instance with radius 2. And now we can do for object in objects. If let object with area equal object as has area, then we print the area. Otherwise, we print something that does not have an area. So just like types, we are basically downcasting the object into has area and optional. And if the object conforms to has area, we will print the area. Okay. Optional protocol requirements. You can define optional requirements for protocols. These requirements don't have to be implemented by types that conform to the protocol. Optional requirements are prefixed by the optional modifier. As part of the protocol's definition, optional requirements are available so that you can write code that interpolates with Objective-C, interoperates with Objective-C. Both the protocol and the optional requirement must be marked by the @Objective-C attribute. Note that the Objective-C protocols can be adopted only by classes that inherit from Objective-C classes or other Objective-C classes. They cannot be adopted by structures or enumerations. when you use a method or property in an optional requirement, its type automatically becomes an optional. For example, a method of type int going to string becomes int going to string optional. Note that the entire function type is wrapped in the optional, not just the return value. An optional protocol requirement can be called with optional chaining to account for the possibility that the requirement was not implemented by a type that conforms to the protocol. You check for an implementation of an optional method by writing a question mark after the name of the method when it's called, such as some optional method, question mark, some argument. For information on optional chaining, see my lecture on optional chaining. The following example defines an integer counting class called counter, which uses an external data source to provide its increment amount. So this data source is defined by the counter data source protocol, which has two optional requirements. So at Objective-C protocol counter data source, at Objective-C optional func, increment for count int gives an int, at Objective-C optional var, fixed increment, int. And so the counter data source protocol defines an optional method requirement called increment for count, colon, and an optional property requirement called fixed increment. And these requirements define two different ways for data sources to provide an appropriate increment amount for a counter instance. Strictly speaking, you can write a custom class that conforms to a counter data source without implementing either protocol requirement. They're both optional after all. Although technically allowed, this wouldn't make for a very good data source. The counter class defined below has an optional data source property of type counter data source question mark. So class counter var count equals 0, var data source is counter data source optional, func increment if the let amount equal to data source optional dot increment optional for count colon count, then count plus equals amount, else if let amount equals data source dot fixed increment, then count plus equals amount. The counter class stores its value, current value, in a variable property called count. The counter class also defines a method called increment, which increments the count property every time the method is called. The increment method first tries to retrieve an increment amount by looking for an implementation of the increment for count method on its data source. The increment method uses optional chaining to try to call increment for count and passes the current count value as the method's single argument. Note that the two levels of optional chaining are at play here. First, it's possible that the data source may be nil, and so the data source has a question mark after its name to indicate that it's optional, and should be called only if data source isn't nil. Second, even if data source does exist, there's no guarantee that implements increment for count because it's an optional requirement. Here, the possibility that increment for count might not be implemented is also handled by the optional chaining. The call to increment for count happens only if increment exists, that is, if it's nil. This is why increment for count is also written with a question mark after its name. Basically, optional chaining, which we talked about in the optional chaining and multiple levels of chaining, because we've already discussed all this in another optional chaining lecture. So after calling increment for count, the optional int that it returns is unwrapped into a constant called amount using optional binding, again discussed in the optionals and optional chaining lectures. If the optional int does contain a value, then that is, if the delegate and method both exist and the method returned a value, the unwrapped amount is added onto the stored count property and incrementation is complete. If it's not possible to retrieve a value from the increment for count method, either because data source is nil or because the data source doesn't implement it, then the increment method tries to retrieve a value from the data source's fixed increment property instead. The fixed increment property is also an optional requirement, so its value is an optional int value, even though fixed increment is defined as a non-optional int property as part of the counter data source protocol definition. Here's an example of the counter data source implementation. We can have a class 3 source which implements or conforms to an NS object, and counter data source and let fixed amount equal 3. So we will increment by 3's as our fixed increment, and var counter equal counter dot data source equals 3 source for underscore in 1 to 4 counter dot increment. So we go from 1 to 4, so we get 3, 6, 9, and 12. We print it. The code above creates the counter instance and the 3 source instance and calls the counter's increment method 4 times. Here's a more complex data source called toward 0 source, which makes the counter instance count up or down towards 0 from its current count value. So func increment for count goes to int. If count equals 0, return 0. Else if count is less than 0, return 1. Else return -1. So if it's a negative number, we'll return +1. If it's a positive number, we'll return -1, trying to move towards 0. As in our incrementation, we start here with -4 and then move towards 0. So we'll go -3, -2, -1, 0, 0, 0, 0. And protocol extensions. Protocols can be extended to provide method and property implementations to conforming types. This allows you to define behavior on protocols themselves rather than in each type's individual conformance or in a global function. For example, the random number generator protocol can be extended to provide a random bool method which uses the result of the required random method to return a random bool value. Extension random number generator func random bool gives return random if it's greater than 0.5. So this way, if it's less than 0.5, will just be false. If it's more, will be true. So we are returning a random bool. Now, by creating this extension, we can use it. We can generate random numbers, or we can generate random booleans, random bool. Now, providing default implementations. You can use protocol extensions to provide a default implementation to any method or computed property requirement for that protocol. If a conforming type provides its own implementation of a required method or property, that implementation will be used instead of the one provided by the extension. And so the protocol requirements with default implementations provided by extensions are distinct from optional protocol requirements, although conforming types don't have to provide their own implementation of either. Requirements with default implementations can be called without optional chaining. For example, the pretty text representable protocol, which inherits the text representable protocol, can be provided a default implementation of its required pretty textual description property to simply return the result of accessing the textual description property. Extension pretty text representable var pretty textual description :string return textual description. Now, adding constraints to protocol extensions. When you define a protocol extension, you can specify constraints that conforming types must satisfy before the methods and properties of the extension are available, and you can write these constraints after the name of the protocol you're extending using a generic where clause as described in generic where clauses. So here we have extension collection where iterator.element is text representable. So var textual description has to be implemented, and so that's defined here as a string, let items as text, self.map $0.textual description return, and then in square brackets items as text.join by separator comma. The textual description property returns a text description of the entire collection by concatenating the representation and putting them in brackets. Consider the hamster structure before. Let Murray the hamster, hamster named Murray. Let Morgan the hamster, Morgan. Morris the hamster, hamster named Morris. And then let hamsters equal, and then creating a array of the different hamsters. And because this conforms to a collection, the array conforms to a collection, and the array's elements conform to the text representable protocol, the array can use the textual description property to get a textual representation. And so we can print the hamsters.textual representation as a hamster named Murray, hamster named Morgan, hamster named Morris. And if a conforming type satisfies the requirements for multiple constrained extensions that provide implementations of the same method or property, Swift will use the same implementation corresponding to most specialized constraints. And that is it for protocols. Thank you.